Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. We're actually starting a new unit today, and we're going to focus on solids. So in our previous unit, we focused on two-dimensional figures, finding areas, perimeters, stuff like that. In this unit, we're going to focus on three-dimensional figures. We are going to be working with volume, and we may work with surface area a little bit as well. This lesson is pretty long. There's a lot of vocab, and I am introducing a bunch of new concepts. And then during the rest of this unit, we'll kind of dive into more of them a little bit more intensely. So a lot thrown at you today, just because there's a lot to talk about when it comes to solids. Let's get started. So when we first talk about a solid, we can talk about the face of a solid. This is a two-dimensional surface of a solid. So a 2D surface of a solid. And you can see on our diagram, if I thought about this as a box, the top side of the box, or the top surface, would be considered a face. Right? And we have other faces. Right? This side of the box would be another face. We could have the bottom of the box being a face. Right? And you could keep going. Every single side of the box would be considered a face. Now, an edge is the intersection of two faces. So an edge is the intersection of two faces. If you think back to possibly our very first lesson, we talked about the intersection of planes. Right? Well, a plane is a two-dimensional surface, and the intersection of a plane is a line. So if we're intersecting two planes that are not extended indefinitely, two planes with actual dimensions, well, they're going to intersect at a segment. The vertex is the intersection of three or more faces. Three or more faces. So the intersection of two faces would be an edge or a line segment. The intersection of three faces would be a point, one that we call a vertex. You can see, all the different vertices, which is the plural form of vertex, on this box. And you'll notice that every single one of them connects to three edges. It could be more than three, depending on your shape, though. All right, let's jump into some of the types of solids we can have. We can have what we call a general cylinder. Now, the cylinders that you're familiar with, the cylinders that you talked about in middle school or a pre-algebra class, you're very familiar with this type of cylinder. Now, this is a cylinder, and it's a general cylinder. But it's not the only type of general cylinder. A general cylinder, by definition, is a solid with two congruent and parallel bases. Those bases are connected by congruent parallel segments. So basically, I can have whatever shape I want for my bases. Right? I could even have something like this. You may think, Mr. Fawcett, this isn't a cylinder. Well, by definition, though, I have two bases that are the same, that are congruent. In this case, they look like rectangles. And these rectangles are connected by a bunch of congruent parallel segments. There's actually an infinite number of them. I can't draw an infinite number, but I could sketch out a few. Right? If I just connect these bases with congruent parallel segments, and you could think if I had an infinite number of these, well, I would eventually fill out that space, fill out the cylinder. So general cylinders, the only criteria, right, is that the bases are congruent. So what I cannot have would be, I could not have, I'm still in my line tool. right? This would not be a cylinder, because the bases are not congruent. So as long as the bases are congruent and they are parallel, we're going to have a general cylinder. Let's look at some specific types of cylinders. Well, if I leave off the word general, then I have what you guys know as a cylinder, right? If I leave off the word general, then I have a cylinder, and this is with circular bases. So if the bases are circular, then we don't have to use the word general, we can just say cylinder. They still need to be congruent, they still need to be parallel. The only thing we're adding to our criteria is that they are circular. A prism is a general cylinder with polygonal bases. So again, it's kind of what I drew up above, except here they're triangles rather than rectangles. But these bases are congruent, and they are parallel. Well, that makes this a general cylinder. But since the bases are polygons, we call this a prism. So prism describes any general cylinder that has polygonal bases. Cones, specifically general cones. So right, when you're, well, I guess I can just look at this picture, right? You guys are familiar with this type of cone. But we have general cones, which can look a little different. The definition of a general cone is that there's a base and a point somewhere that's not on the base, and then we draw as many, and when I say as many, I mean infinite, an infinite number of segments from the point to the base. So you could have a weird base shape like this. I could have I could just do another rectangular base. And I could put my point wherever I want. I could put it directly above. I could put it all the way over here. I could put it below. It's all about frame of reference. So if I pick any of these points, I'll choose this, wacky one over here. Right? If I connect this point to every possible point on the cylinder, not just the corners and not just the edges, but every single point that's inside of that rectangle, well, I would eventually have a cone. But again, I'd have to draw an infinite number of these segments to fill out my shape, to make it a solid. So general cone, any shape base is okay, and there needs to be a point off the base, and the two are connected with segments. Notice that the segments are not parallel in this case, right? Because they all intersect. They all intersect at that point that's not on the base. All right, if you take off the word general, then you're left with what you guys have known as a cone. And this is when it has a circular base. A pyramid. Well, just like a prism was a general cylinder with a polygonal base, a pyramid is a general cone with a polygonal base. So, it's got to have a square or a triangle or a rectangle or a hexagon, etc. Some polygon as its base. Now, there's two more vocab words we can use to describe these solids. A right solid, so a right cylinder or prism, is one where the faces are perpendicular to the bases. So if you notice, if we look at this cylinder right here, there's a right angle between the sides of the cylinder and the base. If I had a right prism, well, let's draw the right prism. Again, I'm just going to use a rectangle. Those are generally the easiest to draw, it seems like. So a right prism, same idea, right? There would be right angles between the base and all of the faces, right? It doesn't matter which one, they would all be right angles. It's a little different for a cone and pyramid, right? You're not going to get right angles with the faces or the sides and the base because all of those segments in the cone are going up to one point, so they're not going to form right angles. It's possible that some of them did. I know I'm going off on a little bit of a tangent here, but let's say our cone looked like this, and our point was right here. Well, if our point was right there, then yes, there would be some right angles. When I say some, this one right here. But if we look at the other sides, right there wouldn't be. Right? It's just right there that there'd be a right angle. Everywhere else, there would not be right angles. So that is not how we define a right cone or pyramid. How we do that is we look at the point that is not on the base. So if we look at this point of this cone that's not on the base, if that is directly above the center of the base, then this is considered a right cone or a right pyramid. So what you could think of, if you drew this down to the exact center and there was a right angle there, then that would be considered a right cone or a right pyramid. An oblique cylinder, prism, or cone or pyramid is, well, one, if we look at the prisms and the cylinders, there are not going to be right angles formed between the faces and the bases. So if I look here, not a right angle. You can try to make it look like one, but that's not going to be 90 degrees. Maybe let me draw that in a little bit better for you. The 90-degree angle would look like that, and we can clearly see that those faces do not make right angles with the bases. For a cone or a pyramid, all we look for is whether the point is somewhere off of the center, right? So remember I said you could think about if you drew a segment down, I may have said line before, I should have said segment. If you drew a segment down to the center, it should form a right angle. Well, this clearly doesn't, right? This right here is not a right angle, so it is not a right cone. It would be considered an oblique cone. A lot of vocab thrown at you. Again, the more we see these, we'll use the right terminology as we move throughout the unit. But these are the different words we can use to describe solids, which are three-dimensional figures. All right, let's move on to what we call cross-sections. And this is actually really interesting, and it seems like it was a fairly big part of your map test. Maybe not for all of you, but when I took it, when I looked at it, there was quite a bit of info on cross-sections. So we need to definitely hit these pretty hard. Plus, they're just interesting to think about. A cross-section is the intersection of a three-dimensional figure, a solid, and a plane. Think of it. It says this. That's why I'm stumbling up. Yours says think. But think of it as what the inside of the surface looks like when the solid is sliced a certain way. So you can think about, what if you just took a knife, and maybe some of you used to play that game. There was a game on your phone where you used to slice fruit. Ninja Fruit? I don't know. I'm probably butchering it. But there was a game where you just used to slice fruit with your finger as you moved it across the screen. And this is what I always think of when I think of cross sections. So pretend you just take a knife and slice through your solid and kind of open it up. Well, the cross section is what you'll see is the plane, is the two-dimensional surface that you see when you open it up. So if we think about this, if I slice this, and I'm looking at this solid right here, if I slice this triangular pyramid through parallel to the base, well, I'm going to end up seeing a triangle inside. In this case, that would be the cross section, a triangle. Now, this is not the only way that we could slice a triangular pyramid, right? I could slice it vertically. I could slice it vertically through the vertex. I could slice it vertically not through the vertex. Let me give you an example. I really feel like this unit helps me perfect my sketches. Maybe you think they're awful, but they've come a long way since my first year teaching, that's for sure. So let's say there's my, in this case, we could call that a square pyramid because the base is a square. Now, what if I slice this vertically? So I take my knife and I just slice vertically down like this. Well, if I start to cut, I'm going to get something that looks like this, and it may actually be a little bit hard for you to tell what that shape is. It may look like a square, it may look like a rectangle. It's actually neither of those. Maybe think about spinning that towards you to maybe help you see the pink shape a little bit better. I'll give you pause the video, see if you can figure out what that is, and then I'll draw it another way, and maybe that might help you. Okay, so keep your guess in your head. I'm going to draw it so we sliced it facing us. So let's say I sliced it, but I went through this part right here and I came down. Well, when I come down, I'm going to get something that looks like this. I think now it's pretty clear what I'm gonna get, right? I'm gonna get a trapezoid. So whenever you slice a figure can have many different types of cross sections. Like, it depends on how you slice it. If I look at this, let's look at the cylinder over here, because I think this first one's pretty obvious. If I slice a cylinder parallel to the bases, right through the center, well, I'm going to get a circle. And maybe you notice a pattern here. Maybe if I slice a pyramid or a cone or a cylinder parallel to one of the bases, well, my shape is going to be in the shape of the base. You know, maybe bigger or smaller, right? If we have a pyramid, it's going to be a similar figure, but the same shape. If it's a prism or a cylinder, maybe let me rephrase it. Sometimes I lose my train of thought and think I said something incorrectly. If it's a pyramid or cone, you're going to get a cross section that looks similar to the base, right? Just a different size. If it's a cylinder or prism, you're going to get a cross section that is congruent to one of the bases. Right? And this is only if you slice parallel to one of the bases, or both. Now, this is not the only way you could slice a cylinder. Let me give you another one to think about. What if I sliced a cylinder vertically? So again, I'm going to slice straight down. I'll take a second. Maybe you want to try to sketch it out. If I slice straight down, what type of shape do you think I'd get? Well, my knife would come in here through the top. Maybe I need to do this on a little bit of an angle to help you really see it. Oops. So I'm still going to slice straight down, but I'm going to do it on an angle. It's not going to change the shape. So I'm going to get something that looks like that. that ends up being a rectangle. So we'll do some more practice with these in class. I'll throw you a figure. I'll tell you how we're going to slice it, and you've got to try to visualize that cross-section. But again, these are just, I think these are interesting. You're taking a three-dimensional solid, you're slicing it and coming up with a two-dimensional figure. Moving on, though, let's talk about nets. A net is a two-dimensional diagram of the surface of a three-dimensional solid. So think about, when you receive a gift or a box, and I know my dad always used to be like, well, he didn't call me Mr. Fawcett, but, he said, son, go take that box out to the trash and make sure you knock the air out of it, right? Well, what he essentially meant was form a net out of the box. He meant to peel the sides down and flatten the box so that didn't take up, half the trash can, and we could fit more stuff in there. So that's kind of what a net is. If you kind of peel off the sides of your solid and you lay it flat with all the different faces showing, what would it look like? And you're going to need to think about these both ways. I may give you a net. Again, these are both nets, and you may have to tell me what the solid is, right, if you build it back up into a solid. Or maybe I give you a solid, and you think about what the net would look like. That's far less common. You're generally going to be given the net and asked, what does the actual solid look like? So pause the video. See if you can figure out what both of these solids would be, and try to use correct vocab. Try to be as specific as possible with the names of what these solids would be when you put the nets together. Okay, so on the left, I'm going to sketch this out for us. We would get something that looks like this. Again, the faces are rectangles, the bases are triangles, and this is a right triangular prism. If you said triangular prism, that's close, but I think it's clear that there would be right angles here between the faces and the base, which means we can throw the word right in front of it. If I come over here, our base ends up being a square. It does look like this vertex up here is indeed directly above the center. So again, we can say right, square, pyramid. Right square pyramid. Again, we'll do some more practice. These are just two types of nets. We could break any of the three-dimensional solids we have down into a net, and we'll, again, take a look at more examples at a future date. We're going to save these practice problems. We're not going to do those right now. We are going to talk about revolutions, specifically solids of revolution. And I'm actually not going to do these problems for you either. I'm going to create some new problems for you, so I don't necessarily waste the ones in your packet. So to create a solid of revolution, we have to draw an axis. Let me just draw one for you right here. So that's going to be our axis. That's what we're going to revolve the two-dimensional figure around. Now you can pick any two-dimensional figure you want. Let me pick I don't know, let's do a triangle. So let's think. If I just say you spun this triangle around the axis, right? What would the solid be that is formed? Well, to think about this, you take every point on your triangle and you revolve it in a circle around the axis. So this would come all the way over to here, and then it would come back again to there. So that single point would create this circle. And you do this with every single one. So same distance on one side, same distance on the other. And again, there's an infinite number of points. We're only going to do a couple. This point would just stay, right, because it's on the axis. And then hopefully you can kind of see the shape. Whoops. You can kind of see the shape that's created, which would be a cone. Right? We can name this specific. This would actually be a right cone because the vertex is directly above the base. Let's do another one. Let's make my axis vertical this time. And let's do a long rectangle. Think about this. It looks like a flag, right? If you just spin a flag around a pole, a rectangular flag, think about what the solid of revolution would be. Well, I'm going to take this point, going to revolve it around. And again, the better of an artist you are, the better your picture will look. I'll do this point down here. See that different color actually. When you're drawing three-dimensional figures, if you're going to be unable to see a line, right, when it's filled up, you draw that in a dashed color. So theoretically, here I would want to change some of these. Just perspective. Because when the shape is filled in, I'm unable to see those dashed lines. I can see the entire base, but I can't see the other parts of those circles. I don't think we need to do any more for this flag problem. I think we can see what type of figure we have. Right? We have a cylinder, specifically a right cylinder. We can throw the word right on here. Again, it really depends how specific they want you to be. If it's a specific question about naming a figure, like on a test or exam, yeah, you're going to want to be as specific as possible. If you're just throwing around the term to identify, are we talking about this versus that, during class or on a piece of paper, you can get away with saying, okay, I'm going to look at the cylinder here, or I'm going to look at the prism here, right? If there's an oblique cylinder and a right cylinder on your paper, well, then it would make sense to say, let's look at the right cylinder. Or if there's, a square pyramid and a triangular pyramid on your paper, well, then you'd want to identify the pyramid by the base, right? So it just kind of depends how specific you need to be. No, not every time will somebody say, right cylinder, unless they need to say right to differentiate this cylinder from some other cylinder. All right, let me give you, I know this video has gone a while, but let me give you one more interesting example as far as solids of revolution go. Because those two are pretty basic, and we definitely need to start off basic, but then we can think about some cooler examples. Let's think about this circle. If I revolve this circle around that axis, think about what I'm going to get. And I may leave you here. I may actually end the video without actually telling you, but it's something you can think about, and you could even Google it if you wanted to. It's out there. and you could see someone draw themselves. But I'd encourage you to try it on your own. Think about what figure you may get. And it may not be a figure we've talked about, right? It may not be a cone or a cylinder or a pyramid. Maybe something new. Maybe it's going to be a familiar shape to you in everyday life, but it's not necessarily going to be a shape that we've talked about how to name using geometric terms. So I will leave you with that. As always, enjoy the rest of your day, and we will look forward to seeing you next time.